So let's start the proof of the KAIST theorem that the determinant of a skew symmetric matrix A is same as its Papian squared. So what we know about determinant? So we know that the determinant of A is summation of all over all permutation. We consider the sign and we multiply all ai sigma I. So let's first say let Fn be the set of permutations in Sn with at least one fixed point. So here we made this bijection. And then as before, this Papian is intuitively similar as taking ordered pair of the perfect permutation, perfect matching. And determinant is, philosophically, we sum over permutations. And then this pair of perfect matchings is corresponded to the permutation with all cycle lengths even. But determinant is summing over all permutations, so there should be some permutation with odd cycle or fixed point. So we want to show that those terms doesn't really matter for the case when A is skew symmetric matrix. So let's first deal with the case where the permutations have at least one fixed point. Then what do we have? If the sigma has a fixed point I with sigma I equals I, then what do we have? This term ai sigma I is actually 0, as ai is 0 in a skew symmetric matrix A. Because this is skew symmetric, the diagonal entries are all 0, so this is just 0. So when we compute the determinant, here it's running over all permutation, but we can forget the permutation in Fn. And let's consider the next case. If sigma is not in En, not in Fn, then it means that it doesn't contain any fixed point, but it has an odd cycle. The permutation has an odd cycle. Then take the odd cycle. So out of all cycles, we choose one, which involves with the smallest number. So for example, if you have two odd cycles, this is a 5, 12, 4, 3, 7, 6, 15, 9. And in this permutation, let's say we have this. Then we choose this as a C because it involves with the smallest number, which is 3 out of this. And let's say 1, 2 are in here in an even cycle, then 3 is the least one involving in odd cycle. And what we do, we reverse the cycle. So now instead of this direction, we consider the other direction. Let sigma star is the new permutation which we obtained from reversing the cycle C. Then one easy thing is that if you take this star twice, then it's the original permutation. Because here we reverse the cycle C, then we get sigma star. Again, in sigma star, if you choose the odd cycle involving the smallest number, then it's the same cycle. You reversing it again, then you get the original permutation sigma. And what do we know? We know more about this as if you compute this term for sigma and for sigma star. It's same up to sign. Its sign changes. Because here, this is the A12 times A45 times A512 times A124 times A37, A76, A93. So these terms all stay same, but last 5 terms, each of them becomes instead of A37, it becomes A73. So everything here is flipped. If you move from sigma to sigma star, these terms flip the sign, but how many terms flip the sign? Odd number of them. The terms which flip the sign, those are the ones involving the cycles in C. But C has odd length, so odd many of them flip the sign, so the sign changes. Hence, what do we have? We know that when we compute the determinant, this can be divided into 3 sums: sigma in En, sigma in Fn, sigma in none of that. And we know this part is 0. And then here, we know that sigma star and sigma are different because it doesn't have a fixed point. So this odd cycle has length at least 3. Once you reverse it, you get a different permutation. So all the permutation in here, you can pair them up. Pair them up in a sense that they are star each other. And then for those terms, we add this term. And I forgot to mention one. And once you flip this, flip this permutation, flip this cycle, the permutation changes. And then from, say, here to here, if it changes, then you can actually check the number of permutations that you need to take, which is even. So sine of sigma is same as sine of sigma star. So once you pair them up, then the term related to the first one and the term related to second one, these terms cancels each other. So this part, every number cancels each other, and then result is 0. So hence what we know is that determinant of A is actually, you only have to sum over all permutation in En only. And on the other hand, what's the Fabian square? Pfaffian square is summation of all weight of m times weight of m prime, where m comma m prime runs over all curly m times curly m. And then we know there is bijection between this En and m by m. So now let's use that bijection to actually show that these two are the same. So we consider a permutation sigma with T sigma is m comma m prime, and let C1 to CK be the cycles which is even, has even length, cycles in sigma. So these are cycles in the permutation. So let's say we have 4, 5, 1, 11, 8, 3, 2, say 6, 7, 10, 9, 12. Let's say it's going to this way. So what? Sigma is $11. No, okay. So this is sigma. So what we do is by writing the elements in each cycle in turn, starting from the lowest number, we obtain a permutation rho for m. So now what we want to do is this Pfaffian is summation of weight, and then this weight is defined in this way. So in the definition, we pair up these pairs in each block. So for given this permutation sigma, we have this disjoint union of even cycles and matching. From there, we want to get the permutation which defines M. How? Here, let's say this is C1 and C2 and C3. Then we start from C1 and we choose the lowest number. And then you write it in a way, 1, 11, A3. And then you move to the next cycle, C2. So C1, C2, C2, C3 could be, I mean, you can order in any way. It's not really important. And here, again, the lowest one is 2. So you write 2, 12, 9, 10, 7, 6. And then here, short one is 4, 5. Then you get this low. Then in this low, as our definition of the weight, so this block, this block, this block, this block, this block, this block give these matching M. And one good thing about this specific choice of rho is that if you let rho prime be the composition of this sigma and rho, then this is actually permutation for M prime, because what's rho prime? Rho prime is if you apply this sigma, then this 1 goes to 11. And 11 goes to 8. 8 goes to 3. 3 goes to 1. So these edges are now shifted to these edges. Again, 2 goes to 12. 12 goes to 9. 9 goes to 10. 10 goes to 7. 7 goes to 6. 6 goes to 2. So now these are matched. And these become 5 and 4. So this becomes composition of this sigma and rho. So what it means is that when we have just weight M and weight M prime multiplication, we don't have any connection between this and sine of rho, this term. Even if T connects this M comma M prime with this sigma rho, we don't know the relationship between these two. So once this is positive, is it positive? Once this is negative, is it negative? But now we have some specific permutation corresponding to this, rho and rho prime. From that, we can actually predict how the sign changes between these two. Then, what do we have? Then, sine of rho prime is same as sine of rho times sine of, let's write sigma first. Sigma times sine of rho. Then what do we have? The weight of M times weight of M prime is sine of rho times sine of rho prime, and we multiply all this, because what's the weight of M? Weight of M is sine of rho times a sub 1, 11, a sub 8, 3, so according to this. And then you multiply this term. And also, weight of M prime is you multiply the remaining term. So here you have to take A45 and A542. both, so you have to multiply both. So this actually multiply all the terms a sub I, sigma I. And what do we know? Because of this, if you plug that in, sine rho square is just 1. This is same as sine of sigma summation, from multiply all these. And this term looks awfully familiar, as that's exactly this term. And then summation is over all m comma m prime, which has one-to-one relationship to this sigma in E. So we conclude that determinant of A is Papian square. So this and this are same. So this proves the theorem. So this shows that Papian is actually easy to compute. But we have to also show that, at least for some graphs, we can give the orientation so that the Papian actually counts the number of perfect matching. So what kind of orientation what we want? Let's say orientation of a given undirected graph is a Papian orientation of graph G if any two perfect matchings M and M prime of G satisfies that both have the same weight. So this orientation gives you a skew-symmetric adjacency matrix. And with respect to that skew-symmetric adjacency matrix, you define this weight, then every perfect matching has the same weight. If this is same weight, this is either all 1 or negative 1. So up to sign, you can compute the number of perfect matchings. But obviously, you cannot hope for having Papian orientation for every graph. For example, it's not too difficult to actually check that the K33 has no Papian orientation. Actually, I have never checked it, so I'm not quite sure whether it is not that difficult to check. But I heard people saying that it's not that difficult. So maybe you can try for yourself. But although not all graphs have Papian orientation, but there are some graphs that have Papian orientation. So for example, one of the theorem by Castellin shows that every planar graph has a Papian orientation. So in next video, we will prove this.